Class, now we will start chapter 12, dealing with vectors. So vectors are different than calculus, different than probability and statistics, different than sequence and series. It's its own thing. So there's no direct link between this and calculus. You're gonna have to shift your mindset a little bit now when we're dealing with vectors. So what is a vector? Vector is just a quantity that has size, which we'll call as magnitude. Size and means in terms of length and direction. So examples of vectors are displacement and velocity. Now, a scalar is a quantity that has size but no direction. So these would be like distance and speed. So we're not going to get into the applications quite yet, but that's what a vector is. Now, when dealing with vectors, we can talk about unit vectors because again, we're going to get to a point where the size, the magnitude of the vector, and the direction are very important. So there's different ways to represent the direction, which we're going to talk about. So a unit vector in the direction of the x-axis, we're going to use with the variable I. And it's not really a variable as in like an independent variable, 2x plus 5, the x that we're solving for. I is really just representing the direction that we're going. So if we're going in the x-axis, we're going to attach an I to it. So we can do it in the column form here, where I is equal to 1, 0. And then 3 dimensions, it would be 1, 0, 0. So that means we're going to be moving 1 unit in the x direction, and then we're not moving any units in the y or eventually the z direction. Now, the unit vector in the y-axis would be with the variable j, but again, it's going to be attached to it, just showing direction. So if we're only moving in the j-axis or the y-axis in terms of j, are in 2 dimensions, we'd say 0, 1, 3 dimensions, 0, 1, 0. Now, if we start thinking 3D in the direction of the z-axis, we're going to use the variable k to denote that we're going in the z-axis, and it'd be 0, 0, 1. The vectors I, j, and k are called base vectors. Again, those are not variables we're solving for. Those are just what are going to be attached to numbers to tell us which direction we're moving. So if we wanted to represent a vector, so consider the points. A is at 2, 3. B is at 5, 7 on the Cartesian plane. All right, so if we were to think about this, this moved over 3 units and up 4 units. Okay, to get from A to B, we moved over 3 and up 4. So with vectors, the idea of going in a straight line between 2 points is important, but also other routes we could take to get from point A to point B. We could represent our vector, we're going to say A to B with an arrow above it. So I would read that as A to B, that I'm moving from A to B, and I went 3 units horizontally, 4 units vertically. So the x-axis and then the y-axis. So I'd represent it as 3, 4. We could also represent it in unit vector form to be written as 3i plus 4j. So again, these are not I and j are not variables we're solving for. I and j represent the direction that we're moving. Okay, and again, those are base vectors. In 3 dimensions, so now say we had some vector, this is just arbitrary because there's no numbers on here, say 3, -2, 1. So we know that 3 represents the horizontal x, the -2 is the y, and the 1 is the j, or the z-axis. Well, we would represent this in unit vector form and say 3i minus 2j plus k. So again, that would just be representing the direction that we're moving. So 3 units in the I direction, 2 units in the J direction, 1 unit in the K direction. Now, magnitude. So this is a big deal to go along with vectors. So the magnitude of AB is the length of the vector, and we're going to denote that with what looks like absolute value bars around it. So whenever you see those, what looks to be absolute value bars, it's talking about magnitude. if we were to find the magnitude of AB, all it is using Pythagorean theorem. And so we could take the square root of 3 squared plus 4 squared, which is square root of 25, which ends up being 5. So the magnitude of vector AB, we would say, is 5. All right, and so they represent this in 2 dimensions, but also in 3 dimensions. We can find a magnitude in 3 dimensions by just taking the square root of a squared plus b squared plus c squared would get us our magnitude. Now to compare vectors. If we want to compare, well, are the vectors equal? Are they negative? Are they parallel vectors? So on here, 2 vectors are equal if they have the same direction and the same magnitude. So both of those have to be satisfied. Same direction and same magnitude, meaning their I, J, and K components are equal to, and so their column vectors are equal. Column vectors is how we wrote it as AB was 3, 4. That's considered a column vector. So if we were to consider the following, vectors AB and PQ over here are pointing in the same direction, so that means they're parallel, and have the same magnitude, so therefore we would say those are equal. But now vectors AB and MN have the same magnitude, they're the same length, but different directions, so we would not say those are equal vectors. So AB does not equal MN. If we were to look down here, AB is 2 to 5, MN is -2, -5, so AB is actually the negative of MN. So this is called a negative vector. All vectors we can write in the opposite order if we write it with a negative in front of it. So AB we could also write as a negative BA. So if we're going against it, we would say it's a negative BA. Comparing vectors. So vectors A, B, C, D, E, F are parallel but have different magnitudes. So we can see CD is obviously longer, EF is shorter when compared to AB. And we can even be more specific that CD is actually half of CD. So this is saying 1/2 of CD is equal to AB. So and think of it, it's twice as long. If you took half of it, you would get AB. Now AB equals 2EF, meaning if I take twice EF, we would get AB. So then we could rewrite these and say AB is equal to 1/2 CD and AB is 2 times EF. 2 vectors are parallel if one is a scalar multiple of the other. Okay, so in this case, up here we had 2 and we had 1/2. Those are multiples of each other. So we could still say they are parallel. We would not say they are equal vectors, but they are parallel because they're scalar multiples of each other. All right, we introduce a new variable, this cursive K. So not to make things more complicated, so we had our unit vectors that were that I, J, and K. This cursive K represents a scalar multiple. So be very careful when you're looking and you see the variable K. Well, is it a cursive K or is it not cursive? If it is a cursive K, it is a scalar multiple. So our cursive K is not the same as our unit vector K. All right. So if there is a scalar multiple, this can also be written as A equaling K times B. Or again, another notation. These bold A and the bold B are another way to represent vectors. So bold A and bold B are another way to represent vectors. You won't see the bold very often except in text. So if you see a bold A or a bold B, that's going to represent some vector. More often than not, though, we'll see it in terms of two variables with a line above it, so because the direction is important. All right, and the last piece down here at the very bottom, vectors AB and GH have the same magnitude. So if we were to find the magnitude of each one, we could use Pythagorean theorem, create a right triangle on each one, and we could find that the magnitude is 29, but these are going in different directions. So we can see with the arrow in the middle there, they're going in different directions. So therefore, they are not equal vectors. All right, so now we can solve for different variables in here to make vectors parallel. So given two vectors, AB is 3i plus tj, so t is represented some variable now that we can solve for, minus 6k. And then rs is another vector, 9i minus 12j plus s. S is a variable we can solve for, times k, where again, k is just representing the direction. Okay, in order for these to be parallel, vector AB has to only be a scalar multiple of rs, so that cursive k. So therefore, 3i plus tj minus 6k is going to be equal to some scalar multiple, this cursive k, 9i minus 12j plus sk. For it to be parallel, we're going to look at each individual component. So therefore, 3i has to be equal to our cursive k times 9i. So they're both going in the I direction, so I don't have to worry about the I. So I can just say 3 is equal to 9k. So for this, 1/3 is equal to k. So now that I know what my k value is, I can solve for some unknowns. So if I wanted to solve to figure out what t is, so tj has to be equal to k times a negative 12j. So t is equal to negative 12 times k, but we know that k is 1/3, so t is equal to a negative 4. And again, lastly, we can solve for the s, so negative 6k is going to be equal to my cursive k times sk. So again, this is where all those k's can get confusing. Negative 6 is equal to s times my cursive k, but I know my cursive k is 1/3. So negative 6 divided by 1/3 is the same as multiplying by 3. So negative 18 is equal to s. So for what values of t and s are these two vectors parallel? S has to be negative 18 and t has to be negative 4 for these to be parallel to each other. Okay, so this is the first part of section 12.1. Work on these problems. Email me if you have any questions, and then we'll start on the next part of 12.1 in the next video.